Good evening, everyone. I'm Jinu Shin, Chief Scientist at RLWRLD and a professor at Graduate School of AI at KAIST. Unfortunately, I can be with you today due to personal commitment, but still, it is a great pleasure to introduce the RLDX-1 today, a vision language action model that aims at human-like dexterous manipulation. This presentation will be delivered by three speakers in sequence. I will start, followed by Myung-Gyu Koo and Dong-Young Kim, the lead researchers on this project. We will walk through three things: why we built this, how we built it, and what we can do. Before getting into the story, let me show you the punchline first. What you are seeing here is the head-to-head comparison between RLDX-1 and the strongest models in the field today: Physical Intelligence Pi 0.5 and NVIDIA GR00T N1.6. The simulation benchmark on the left and real-world benchmark on the right. RLDX-1 set a new state-of-the-art across every single benchmark. And I want to draw your attention to the right side. On the functional capabilities like motion, memory, sensing, the gap is more than 2 times over the strongest baseline. It means that RLDX-1 can do things that existing VLA simply cannot. Let me show you why this matters and how we got this. So let's start with some background. What VLAs are and what's currently missing from them. The hottest topic in robotics right now is a single generalist policy that can handle diverse tasks and environments. Physical Intelligence Pi series and NVIDIA's GR00T N1.X series are the two most prominent examples. Why is this happening now? 2 reasons. First, pre-trained foundation model gives us rich scene understanding and language prior out of the box. The second, public robot data has now scaled up to million episode level. In other words, robotics finally has the data and model to ride the same scaling wave that NLP and vision have been riding for years. So what exactly is a VLA? In one line, a VLA extends VLM style generalization into robotics policy. On the left, regular VLM, vision language model. Given instruction, pick up the apple and place it on the bottom shelf. It can reason in language. The robot has graphs, the apple, the shelf on the right, blah, blah, blah. This shows strong scene understanding of VLM, but no actuator output. On the right, VLA. Same backbone, but now coupled with action head that turns the reasoning into low-level motor commands. The diagram you see here is from NVIDIA's GR00T N1.5. The vision language feature flows through cross-rotation and self-condition into GIT blocks, and the model finally outputs motor actions. This shift is what letting robotics policy finally benefit from scaling low, and is why the field is exploring right now. But here is what we learned from years of putting VLA into real robots. VLA today are not the full story. The fundamental limitation is that they can reason from a single visual snapshot, but real-world manipulation demands more than that. Consider 3 following scenarios. First, motion awareness. Which way should I move to catch this ball? You simply cannot answer from the static frame. You need temporal dynamics. Second, long-term memory. Which object was inside the box? The sequential decision needs historical context, not just current view. Third, physical sensing. Is the plug fitted in the socket? Context-rich tasks like this need touch and force feedback. Vision alone is not enough. So RLDX-1 is the first VLA that integrates all 3 of these functional capabilities into a unified single architecture. Now let me show you how we actually built this. At a high level, we designed 2 essential components of VLA so that it has 3 new functional capabilities as a result. The first component is a new vision language model backbone. Our VLM takes video and language as input and produces historical aware features. 2 of our 3 functionalities live here: motion awareness and long-term memory. The second component is a new action head architecture called multi-stream action transformer. It combines VLM features with physical sensing signals to predict future actions. The third functionality, physical sensing, is here. Now, look at each component in more details, which will be explained by Myung-gyu.
Hello, I'm Myung-gyu, and I'll first explain how we built RLDX-1 VLM, which is our first component. So we basically start with the Q3 VLM as our backbone and fine-tune it on our own robot-grounded VQ dataset. So it basically makes the model to understand what robotics is. And on top of that, we layer two functionalities. First, motion awareness. So here we introduce a motion extractor that explicitly captures the temporal dynamics. Then those motion augmented features are then compressed into a single token so that we can more efficiently process those multi-frame video input. Second, long-term memory. So we also introduce cognition tokens here, which compress the current VLM context. And as you can see here, we merge them with recently cached cognition token features to generate memory feature, which contains long-term historical context. And this unlocks the long horizon tasks that we cannot solve only with a few recent frames. And one more thing, those two functionalities are added as modules on top of a strong base backbone, which means we do not throw away the foundation, we are just extending it. Now, MSAT, which is the most important part of RLDX-1. So the biggest challenge when we build a multimodal robot policy is that the inputs are too heterogeneous. They're deeply heterogeneous. For example, cognition features are made of high-dimensional vision language features, while proprioceptive states are low-dimensional features, while high-fidelity kinematics. But when we just try to handle all of these different signals using a shared parameters, we found that the model easily collapses, which means, for example, the model only sees without sensing, or sometimes the model only tries to sense without seeing. So we extended the architecture idea from image generation to action modeling. So here we designed three separate streams: cognition, action, physics, and each stream handles each modality. And as you may have noticed, our third functionality, physical sensing, lives here. So physics stream takes current physical signals such as joint torque or tactile signals and jointly predict the future tactile signals or future joint torque signals alongside future actions. And this makes our model to internalize the physical interactive dynamics. So how do we train this thing? Let's talk about training and data. We use three-stage pipeline that goes from a generalist to a task specialist. So stage one, pre-training. Here, we leverage large-scale data across diverse embodiments to build our model's general priors over actions. Stage two, mid-training. This is where we inject our three functionalities we explained, while specializing our model for our target embodiments. Stage 3, post-training. Here we apply RL with our adaptive data collection, especially when we try to solve the most challenging tasks. And one last thing is inference optimization. So we achieve about 1.6 times speed up using kernel level optimization techniques, which makes our robot to move smoothly and respond in real time. So I'll walk you through the stages 1 and 2 in more detail. So stage 1, pre-training. To leverage the large-scale dataset across diverse embodiments, we span humanoid platforms along with gripper-based platforms. But here's the problem. We do not have that much datasets of humanoids. But humanoids is one of the most important embodiments we need for dexterous manipulation. So our solution to this problem is synthetic data. First, we generate new videos using video models like NVIDIA Cosmos Predict 2 based on the initial frames of real-world robot demonstration. Then we label them with low-level actions using inverse dynamics models and replay those actions using physics simulators such as NVIDIA Isaac Sim. And finally, we compare those rollouts against the original synthetic data, and only the motion-consistent data survives, while everything else gets discarded. And we found this kind of synthetic data actually brings us a noticeable advancement in humanoid manipulation tasks. And especially, this benefit is maximized when such filtering process is applied. So the lesson here is scale alone isn't enough. What matters is scale of qualified data. And stage 2 is where we try to specialize our model to our target embodiments. So here we choose 2 embodiments. First, Alex humanoid with 5-finger hands and joint torque feedback. Here, we leverage our synthetic data pipeline along with real-world in-house data at 5:5 ratio. Second, Frontier Research 3, a single-arm gripper platform with tactile sensors on its tips. So in this case, we use 2 types of physical signals. First, joint torque, same as Alex, plus tactile signals. So this is where the physical signal supervision enters our model. And from now on, Dong-young, my colleague, will show you what our models can actually do.
Hello, my name is Dong-young, and I will introduce the most exciting part, evaluation. We evaluate our model on diverse simulation and real-world benchmark. Let's move on to the simulation benchmark first. We evaluate our RLDX models on diverse simulation benchmark, and the result is very clear. The RLDX models are performed every sort of baseline, such as pi 0.5 and GRUD 1.6. And let's move on to the benchmark result in more detail. Our models show significantly high performance on class benchmark, such as Libero and Libero Plus and Simpler. And we also observed that our models show the strong performance on challenge benchmark, such as Robotics Kitchen and 01 Tabletop and Robotics 365. Here, I want to highlight 2 things. First, for Robotics Kitchen, we are the first VLA to achieve over 70% on this benchmark. Next, this gap becomes more larger on 01 Tabletop benchmark, which is the humanoid manipulation task. So these results show our models is strong on their humanoid manipulation. Now, Let's move on the real robot benchmark. We evaluate our models on the real world benchmark are designed to evaluate the versatile intelligence and also the functional capability we added, like motion awareness and memory and physical sensing. Our model also outperform our average sort of baseline, and this especially this is pronounced on the benchmark or design for functional capability, like this. So let's go through one by one. Okay, for motion awareness, our model can capture the information about the motion information, so their model performed to adaptively control the robot to catch the moving object. Let's watch the video. The conveyor moved the object in different speed, and our models adaptively control the robot to match their moving object speed in real time. However, the baseline model without support their motion awareness failed this task by grasping too earlier or too late. This is because their baseline model does not support their motion awareness, thus cannot properly estimate the speed of the object for grasping. And this trend is also observed in their similar benchmark that require their motion awareness, like their spin tracking and point gain. So to summarize, our model to compare with the strongest baseline, our models improve the performance by more than 2.2 times. Next, let's move on to the benchmark for long-term memory. Our model can remember the past history for sequential decision making. Let's watch the video. This video shows the baseline model that does not support any memory. The human pick up the box and put the object inside and turn it. And the robot must pick up the box which contains the object. But as far as you can see, the robot failed to grab the object that inside their they failed to grab their box which inside their object. This is because their model has no way to identify the box which ones contain the object. In contrast, the RLDX correctly identified the target box using its memory module. This overall trend is also observed in similar benchmarks that require the motion awareness, like the curve swapping test and cell game. To summarize, our models, to compare with the strongest baseline, our models improve performance by more than 2.2 times. Finally, I will introduce the benchmark for physical sensing. Our model can effectively process the physical information for the fine-grained control. This video shows the robot to grasp the card by using their physical sensing. So the baseline model without supporting physical sensing failed by grabs too hard, but our models is successfully grasp their card by using physical sensing. And this trend also observed in similar benchmark like part to cup pouring task and plug insertion and egg pick and place task. To summarize, our models, to compare with the strongest baseline, our models improved the performance by more than 1.6 times. So, to warm up this presentation, I hand over this mic to Jinwoo Shin.
Okay, I'm Jinwoo. So let me wrap up. In summary, our RLDX-1 changed three things. First, the architecture. Multi-stream design that integrates motion, memory, and physical sensing. This is the first way to bring all three together. Second, the data. A synthetic data pipeline built on video generative model with motion consistent filtering, which address the fundamental data scarcity issue of humanoid learning. Third, the training recipe. A three-stage pipeline that specializes to a robot without losing generalizability. In one sentence, RLDX-1 takes a meaningful step beyond versatile intelligence toward human-like dexterous manipulation with diverse functional capabilities such as motion awareness, long-term memory, and physical sensing. And this was made through a joint effort with the real world and KAIST. Thank you for your attention.